We'll have 90 minutes together, or nearly, 5 minutes late, to deal, talk about the subject of self-models, self-reference. This is a workshop. That means it's not a single talk, obviously. It is a number of people presenting, some of them still up there. Let's still start. And I quickly want to outline the proposal of the workshop. That's the proposed structure. We'll be able to change the structure as well. So, where's my? Okay. I'll start talking about presenting two introductory talks, short ones, relatively short ones, in order to frame the term self-model a little bit, admittedly in the way that we are taking, that we're looking on it. So it will be our definition of self-models, or our frame on self-models. Starting with Metzinger, it's from a very philosophical point of view. So that's a little bit of an experiment, because I'm not a philosopher. I'm an electronic engineer by training. Even though I'm interested in that area. So maybe as an electronic engineer, I've got the credibility of building working systems to talk about philosophy. And maybe I'll try to give it an engineering spin as well. So this is pure philosophy, the first part, relatively short. Then we could have a quick discussion. Shouldn't be too much, shouldn't be more than 5 minutes. I'll probably relatively hard kick in these discussions, trying to get on track then with the other stuff in order to keep with the schedule. So should be short discussions. Then I'll have a talk on these various levels of self-models that we propose. This is split in two parts, this little talk. One is our take on the what is a self-model, on the, as Ben really, we had just had a chat there, said the problem statement. What is actually the problem to look at? So we'll present it from our perspective, and maybe we have a quick discussion there on other perspective of what really self-models are. And then the main part is like going through, again, our 11 levels of self-models. And it's our 11 levels, but there was really interesting discussion here on this conference with guys from OpenCog, from Sigma, and from NARS. So I really, yesterday, we changed this presentation to be completely architectural neutral. So trying to keep it like completely independent of the actual implementation of the cognitive architecture we want to talk about. Let's see if that works, how that works. And then there's a number of people who I asked 2 days ago if they want to participate. So we got some we got some conversations from confirmations from people who want to talk something. I got a video from Paul Rosenblum from Sigma I want to start with, and then Patrick Hammer is going to present 10 minutes here, his perspective on these on these 11 levels of self models. And then, I think Yosha confirmed to me that you wanted to comment something would be very interesting, either on more on the philosophical part or on the cog arc part. And Jose, are you there? You don't want to you don't want to contribute. You get enough work till January. Okay, so that's the rough structure. After this, we're definitely going to discuss. We can have some short discussion in the middle, but I may be relatively. I'm not. Well, yeah, may stop discussions as well if I feel that we need to time for just continuing with the subject. So that's the structure. Where is? This is a very small screen resolution. Okay. I'll start with this talk here on Thomas Metzinger's theory of subjectivity. So we're talking here about the C word, consciousness. We're talking about the Q word, qualia, like redness, the why things feel like they are. And we're talking about a number of other subjects that are like nearly esoterical or well, very philosophical, and there's at least no mathematical theory behind them that might somehow formalize them. So we're in philosophical space. In philosophy, it's already, I would say, my take, it's already sufficient if there's a few people that believe in a certain theory, and but what there is like to defend the philosophers against the mathematicians, there is predictive power in philosophical theories, surprisingly, and I have like not psychological theory, not like cognitive science theory, but philosophical theory. Predictive power, and I'm trying to present it from an engineering perspective. That's a really two very different things apart, and I want to explain what I understand as the engineering perspective here, why philosophy and engineering gets together. Because I'm a guy who wants to build a mind, obviously, like many others here in this room, and as a software engineer, as a trained software engineer. There's my phase model, my implementation model. I start off with a business plan from some company having some problems or whatever. Somebody who wants to throw money at something. Then there is these domain expert, the business analyst, process analyst. They're doing reverse engineering or whatever. There's people who really know the business where this system should actually be applied. So the environment from the non-technical side. And then these guys produce requirement specifications. So all the things a new system or an extended system should be able to do. And then comes the techies and create a design and implementation. So and, as somebody who was interested in the mind since a very young age, I think I learned Prolog with 16 or from a reference manual, because I wanted to understand how this works. So I was looking for this requirement document for a long time. And I didn't really find it in any place. And so I was really surprised when reading Metzinger's theory that an engineer could read this as the specifications document for an artificial general intelligence. So that's my motivation why I find this guy interesting. And so in the next few minutes, I'll try to reproduce his theory. Please, Joscha, if I do like major mistakes, please interrupt me. Get philosophy wrong, then we'll have some more discussion on that later. But before actually diving into Metzinger, SMT, self-model theory of self-model theory, I want to dive quickly in what is hop. There's another whole bunch of theories, higher order theories of mind. So I want to, there's this David Chalmers who brought up this idea of the hard and the soft problem of consciousness. And there's a few others talking about this. Peter Carutha, this slide here is basically put the links here at the bottom, so you can read the original stuff that I'm trying to summarize here, who exposes the problem. So I quickly summarize higher order theory of mind, which is coming kind of before Metzinger, and on which base Metzinger kind of improves, at least in my personal view. So I really start with the most esoteric stuff around consciousness and what this is in terms of hot, higher order perception. So let's start with something very easy here. I got a scratch here. Yeah, I'll try to be very work with pictures. So a mosquito bite me last night, and I got this itch here on my. What did I say? Scratch. Got this itch here on my cheek. So this is a perception, a direct perception. There's several layers of direct perception. If we go into perceptual models, psychological models, or whatever, cognitive science models. So I got let's say, a first order, yeah, in terms of, we use first order logic terms here. I get a first order itch, okay? First order itch, which is moved by neurons, whatever pathways, and perceived and represented in my brain. And then something marvelous happens, that my mental eye is somehow aware, becomes aware, whatever this means. I'm not going to talk about what this means, really. I'm just like just want to work with this later, yeah? So, but we need to talk about it at the moment. So I become aware of this itch, whatever this is. But there is some thought in my mind, that's according to higher order thought theory. There's a thought in my mind, hey, I've got, it's itching there, okay? Oh, I got this thing here. And then, like being like at the age of, I don't know, what is it, 6, 8, or 10, I can even be children, not before, afterwards, children and particularly me, I'm become aware that I got this thought, hey, it's itching. There might be some, stuff around this thought, like associations, ideas on how to remove the need. We just learned this need of removing this itch, and so it's not only like this single thing. There's like it's starting to be bubbly, whatever stuff around, and become aware of this perception process, interpretation process maybe, and then I can even become aware that I'm theorizing about perception processes, and so on. And that is very important. This relationship is transitive, potentially infinite. So one of the characteristics of higher order thought is that there is potentially infinite numbers of meta levels to any first order perception. Okay? So that's hot, basically. So there's people saying, at the moment in which you become, one thing is the first order itch, and then there's this higher order thought about the itch. Yeah. And consciousness, there's this definition of consciousness saying consciousness is when I'm at this higher order thought. Full stop. Very, very nice. This is mathematical, actually, kind of. I think it's wrong, or I don't think it's wrong. To me, it's not very practical, and I cannot read it as a requirement document. So that is my definition of wrong. So it doesn't really tell me how to build a system in order to implement that. Okay, so now I'm looking at variants of this original hot, and I think there's already 10, 12 variants of them, and there's like mixed stuff. So there's a white body. You'll see some links there, and just looking in Google, so you find plenty of work. An important variant is HOP, higher order perception. It's really the same as higher order thought, except that instead of thinking, I think I have an itch, and I think I'm thinking about itches. I say I've got a perception of an itch, and I got a perception of the thinking about the itch thing. So replace thought by perception, and it kind of postulates an inner organ that is capable of looking at the rest of what's going on in the mind. The practical difference for an engineer are marginal. Well, this could actually, an introspection subsystem in a cognitive architecture could relate to that. So the higher order might also be something like an introspection. Anyway, not really predictive power for me. There's more variants. One important one I need to mention here, because it resolves this problem with the possibly infinite number of higher levels. That is the dispositional hot, which says, in order to be conscious, I don't need to think the higher order thought. become aware of the object level, but I just need to be able to, potentially, and then, so when I'm interested, when my attention focus is on that area, I might go higher levels, but that's not always necessary, and that way solves this infinite loop that we might get in there. Okay. Hot hop. Any questions so far? I'm not the theoretical expert. I've just tried to get the problem space here out. So don't nail me down on specifics of the theory, unless you could read them as a requirement document. Okay. And I already mentioned this, one important critique on higher order thought, at least, is reads like this. I got my first order term here, itches face, and this little triangle is like a modal logic operator from epistemological logic, knowledge. It reads, I know. Or you could also use another one, I perceive. Then you would have the, so I know that my face itches is the higher order thought for this itches. So there are people, I don't know really seriously or not from an engineering perspective, that postulate that if you can write that, then this is consciousness. And, obviously not very satisfied with this. So there's people criticizing hot hop, higher order theories of consciousness in general this way. So that's the base with which I want to contrast Metzinger, SMT, self-model theory. And so what's interesting for me in Metzinger's book, there's Being No One is the original work. It's relatively, it's accessible, but it's relatively thick psychology stuff. There's a much more easier readable one that's the Ego Tunnel at the bottom, and you only need to read the first 40 or 60 pages, and he very, very lightly exposes the problem space there. So his theory postulates two important concepts. One is the phenomenal self-model, and the other is the phenomenal model of intentionality relationship. So this is funky stuff. And I got Metzinger for you. I had Metzinger for you. And we had some acoustics problems. Let's see if that works now. Technique. No, we have some important problems here.
First thing to understand, I believe, is that there is no thing like the self.
1 second, I'll try. Okay. Thank you. So I should use this one? For the moment. Okay. Wait. Both. Can you hear this noise? Okay, great.
To understand, I believe, is that there is no thing like the self. The first person pronoun I doesn't refer to an object. Just points to the speaker of the current
Better?
There is no thing in the brain or outside of the world which processes. And of course there is a conscious experience of selfhood.
I think somewhere here. Yeah, the alternative might be to. Well, let's try this again. Can you hear that?
But that, it seems, is entirely determined by local processes. And ultimately, it's a physical
Oh, what a pity.
By the way, you intended for this to be 10 minutes, you're already at 60.
Perfect. Maybe I'll just repeat the important sentences it says.
The first thing to understand, I believe, is that there is no thing like the self.
The first thing to understand is that there is no thing like the self.
The first person pronoun I doesn't refer to an object like a football or a bike.
The first person pronoun I does not refer to an object like a football or something else.
It just points to the speaker of the current sentence.
It just points at the speaker of the current sentence.
And there is no thing in the brain or outside of the world which is us.
And there is no thing in the brain or where outside that is us. I think we can leave it here. It's not a very smooth format of audio amplification. 1, 2, 3. I'm on? Okay. So, but we get the idea. This is Metzinger. He seems to know about his subject. So, yeah. So what he basically wants to say is that, yeah, a brain could be a computer. And that, well, the hard problem of consciousness, the qualia, might not be there, but he envisions, or he tries to describe a theory in which it's actually not necessary to have this qualia, like we feeling redness or whatever, the feeling the things how they are. So, but this could be a kind of emerging phenomenon. What I take from that as an engineer is, okay, one less requirement, and particularly the hard one. So that's, to me, that's good. So then I can focus on what is the easy or functional problem of consciousness, which is a lot easier, at least according to Chalmers. And yeah, and that helps me to build a system, or it's gets me slightly further. So there's a few things I was just writing out of his, like summarizing from his stuff. So this is nothing but a summary. Please read yourself. Everything is a representation. So the reasoning goes like, okay, our brain is a brain, and we have no way to perceive the world or ourselves, a part of the world, directly. But what we perceive, what our internal large neural network is working on, our representation. So there is no direct contact to the world, but everything is a representation. That sounds great to me. It's it's one of the reasons why we went so much on states, on representing like different layers of states, and our scene-based reasoning architecture really focuses on these levels of state and representing structure. That's structure that could really then, well, we'll see. Yeah, we talk about compression, prediction capability. The other point is transparency. Okay, so there's many examples in his books about that this self model, this phenomenal self model PSM, is transparent. That means from the subject perspective of looking at the world and whatever, we do not. We cannot see that there is this. The processing layers that gets us these sensor data interpreted, except for a few pathological situations with people like with a iron pawl through the brain and whatever layer of the brain damaged. So that gives us some idea of like from the errors because of hardware that they're how this representation system could work, and we get some glimpses on the non-transparent part of it. So transparency means this is the reason why we can be conscious even though we're not, or we can have the feeling or qualia experience while we actually don't have it. At least this is in his theory. You don't have to believe this in order to later see how we could build systems. Yeah, representations not only include the external world, but also our internal mental states. This will be the main part of the second talk, and he's got this concept of mine-ness. So this really, I read it as the description, like why we feel like one thing. We feel like one thing, even though he says we're not. Like this leg here. It feels like my leg because I can move it. There's this transparent representation of it that just fits so perfectly in all the other things. So he explains mindness to a great degree, and very much related to this is the phenomenal model of intentionality relationship, which I'm now going to skip because I'm running out of time for this one here. So it's basically part of the self model, and it's more but on the action part and on this subject-object relationship and how this is being represented. So read the stuff. It's relatively easily accessible, and that's this first slide. So I'm trying to. So what did I say? What is the point? There is, as an engineer, there is a representation. That's great. There's some data structures that work together in some way, transparently, so that it provides most of all the, it kind of explains consciousness, or at least the parts that are really interesting me. And it doesn't sound particularly esoterical. That's also important for me. It sounds like pretty German. and yeah, that's. So we took this. Now let's go for the next one. And I'm slightly late already. But we do have time. So now comes stuff from scene-based reasoning, from our Brian and mine intent to develop like the requirement document for a cognitive architecture and some minor implementation to translate the self-model idea of Metzinger into like something that we could represent using high-level building blocks of specific artificial intelligence. So, as a software engineer, or I'm an architect, former architect, I'm used to work on building blocks, high-level building blocks, and they need to fit together. And so when I'm building a large system for like corporations, some whatever data, ERP type of application, I need loads of data from different places, and I need to integrate them into one, typically database. It's not going to help us much here, this database idea. One place, and so I can do all the things I want to do. And yeah, putting things together. So the point is that we took, in scene-based reasoning, we were trying to, what in business you call a best-of-breed approach. So we were looking at like specific building blocks, like a planner, like a reasoning engine, inference engine, like a, for example, plan recognition or perceptory system. So that's the idea, the specific idea of scene-based reasoning. We were taking this from each of these 40 areas of artificial intelligence, whatever 40, depending on how you define them. We were looking at what are the best stuff, what's actually working, what doesn't have these pathologic computational complexities. What is polynomial, basically? What is polynomial, and how could we put them together to make one system that would cover everything? So that was our idea. So the core of this idea is that we were not looking at a single formalism that covers everything, but we're looking at 40 different subsystems, heterogeneous, each with its own data structures, whatever, and we wanted to put them together in order to cover these 11 layers here. So, yeah, the self-model that Metzinger proposes, I'm coming back to the self-model, is split into several layers. These are some layers that we extract from the self-model by basically looking at these subsystems. This is a very subjective approach, so it's no way generalizable, and other cognitive architecture may have different layers of a self-model coming up here that constitute a self-model. I would claim it doesn't really matter as long as there's the general idea of self-model, and however you want to slice and dice it, really doesn't matter in terms of the problem statement for this talk and for this area. We can identify several important, like large-scale areas. One is like the physical stuff here, capabilities like physical capabilities of action. Then there is a planning and goal space. Goals and planning are connected in the sense, if you take a narrow type of goal, then this is what the planner tries to satisfy by creating a plan. It's a very slightly different concept of a goal than the one you just presented. Then what really interests us is the social aspects. Somebody said that one of the biggest failure of artificial intelligence, functional, is not to be able to count for modalities, modal verbs. I want to, I think you want, things like that are, please correct me if I'm wrong, are currently not interpretable really, neither by linguistic theory nor by cognitive architectures or anything like that. So in terms of business terms, we think this is the area, if we manage to come up with something that works in this area as little as possible, we may get some research funds. Anyway, if somebody knows where to get the research funds, please contact me later. So we are actually trying in our work to focus on this area because there's a big hole in there. And then emotional, I'm not really sure about. Historic is so. I'll come to a few more. This knowledge self-model is like introspection and belief hierarchy. So there's a number of levels. I'll explain later. And but what's important is, well, these levels correspond to basically subsystems in any cognitive architecture. I would claim that tries to represent the human brain, because there's evidence, like in terms of phrases. I put some phrases here behind. Evidence that we can talk about it. And if we can talk about something, then we cannot say it's not there. We need to be able to have at least one reasonable theory or system that explains what's happening there when we talk about it. So I put some sound bites here explaining all of these areas. And this is, at this level, the justification why there is such a self-model. So most of these phrases here are self-referential to some degree, but only to a small degree, and that's an important point. Jose, please.
These are all levels because we think some of them depend on other levels, or just levels of ecological characteristics. So is any order?
I repeat the phrase for I don't know if it's being on the loudspeakers, whether these levels depend on each other or whether they're more or less like independently. Is that? Yeah. Because they're called levels, so maybe there's one based on the other. So yeah, technically they are, I would say, to a certain degree, not in a hard way like architectural layers in a Java stack, but and some of them will require processing capabilities of the lower ones. But the important part between knowledge and planning, what we believe is the important part, is actually cyclical, so it's mutually dependent, so you cannot really establish a hierarchy there. It's messy, like reality. Okay. So we got these levels of self-models. We have an engineering justification, for why there are these levels. But it's no problem if you want to, if you put several of them together to make one new one. That's really, it really doesn't matter. And but together, well, together we claim they get close to the self-model for Metzinger, or they could implement at least technically. So there's no strong reasons why not. Could means there is no strong reasons why not, so they could implement the model for Metzinger. So when somebody comes up with a strong reason that it's not possible in one area, that's interesting. Then we should discuss about it. And that is the style of discussion that I would propose, like looking at all the things that failed in the last 50, 60 years of AI, and whenever, for example, whenever there is the need to hand code hundreds, thousands of lines of first order logic, then this is probably something that doesn't work. We want to avoid this. If there is a non-tractable algorithm somewhere, we want to avoid this. So we need to, if we want to go from an engineering point, we need to make sure that any of these areas that we need, that are crucial, should work, or at least there's no strong reason why they shouldn't. Okay, why are these sufficient to explain Metzinger's model, self-model, this one transparent self-model? I don't know. But we propose this as an approximation, and I come up with, together with Jose, we came up with an idea on how to quantify this approximation. It's coming in one of the next slides. So we don't know if this is a sufficient condition, but these are necessary conditions, we believe. And Metzinger, in his book, mentions nearly all of them more or less explicitly. And so there is some evidence that this correlates. Not much more, but engineers also are very people with fantasy. So I now want to I've got two slides on looking at actually what is a self-model. So we've seen there's this theoretical, this philosophical self-model. We've seen probably several layers of it. And so what I'm really interested, what is my personal goal here is in this workshop is like to discuss the idea of, is this self-model with the current narrow AI implementable, which then comes down to, are all of these levels here implementable? What is necessary for them? One of the referees on our paper said, well, you're proposing pretty high-level building blocks that are not yet state-of-the-art. That's right, there is no really working plan recognition component, for example. Is one of the building blocks we're proposing. It's not in here because it's not a self-model. It's plan recognition is like looking at some monkey eating a fruit and then understanding that he's trying, that it probably was hungry. Or train planning, there's travel planners. So plan recognition exists only as a narrow, as a toy domain, narrow AI. So it's not yet there. However, the problem of plan recognition is understood. There are approaches that there's not too much resources being dedicated, so we could say in 10 years we can solve that. If Google puts their resources behind it, then we're probably even there in 5 years or so. So this is the type of reasoning I want to go on building blocks. I want to talk to implement all of these self-models. So we're not yet there, but we just make sure there's no strong reason why it never be possible. Okay.
I have a question about,
please.
or comments about just the notion of implementing these self-models. I mean, that phraseology embodies assumptions about the right approach to take, right? I mean, because there's a spectrum of ways you could get self-models like this to appear in your AGI system. I mean, one would be to somehow write code specifically oriented toward making your AI system model itself. At the other extreme would be just connect a learning system that observes a world and observes a system controlling, for example, a body in the world, and then infers a self-model, just like it infers a model of some other object out in the world. And then I guess there's a spectrum of possibilities in between there. It's kind of similar to other, innate versus acquired debates, just like is syntax something that's supplied in code? Is syntax supplied in is syntax just learned by experience and observing language, or do you have an inductive bias for learning syntax, and do you have a sort of inductive bias for learning a self-model rather than an encoding of the self-model? What would an inductive bias for learning self-models look like? Right?
So I rephrase maybe quickly, coding versus learning, induction, how are these created? My point is, or my intuition is that none of, and from this first little implementations we've done, there will be none of these self-level that will be learnable from scratch, from zero. So, and all of them fall in exactly what you say in between. Pardon? Bootstrap, it's all bootstrap. It's all bootstrap. You need to code some initial capabilities, and only once you get these initial capabilities, and on several of them, then these learning loops could start automatically.
In principle, that isn't true, right? Like in AXI system, or an arbitrarily powerful reinforcement learning system, which just observed the body interacting with the world, in principle, given enough data, I would think would have to be able to, at least implicitly, infer a model of what the system was doing. But it might take too many resources, right?
Yeah. It's probably, let's say, it's
sustainably given feasible space and time resources, then that's too hard of a learning problem.
So
to know some biases.
I agree. Like I don't want to say, I don't want to put any claim or positive or negative whether it's possible to just like purely learn. But I would say, as you, it's probably faster just to provide some initial bootstrap hard-coded stuff, manually coded stuff, and then none of these layers is codable. So that means all of these layers need training, learning, and there needs to be this. Well, it's child AI, so it's that model. All of them need training, and from what I've seen, there's no one that you could code just by hand, or a group, or even a large group could code. So there would be, even though I'm taking like engineering in a kind of symbolic perspective here, so this is, at the end, I would say 99% of all the CPU cycles of a possible system would be burned by neural networks or massive massive data interpretation and machine learning systems. So even though it looks pretty symbolic what I'm talking, I would say 99% of code cycles will go to statistical and the actual dirty work of wading through terabytes of stupid corpus data. So none of these levels are easy. But the point is, again, that how I would like to frame it is make sure there is no like hard constraint why it could not work. So I'm trying to break a really, really complicated problem in 11 still quite complicated problems. That's what Kalmos has, the easy problem of consciousness. So we're at that functional consciousness. So the concept of a self-model, I think we'll get into that further in the discussion. So what is a self-model? What do we understand as a self-model? And that somehow would be able to implement these 11 models and then the one big model is, it's basically coming from Ben's overview paper on cognitive architectures. So obviously there's perception, action, whatever. But we would like flesh out the core that is a mix of planning and knowledge, like knowledge representation, like OpenCog, semantic network stuff. So the combination of both. And yeah, because this deals with temporal structures, timelines, even planning in a very general sense of the planner community. And this talks about inferences, logic, properties of things. And this is our limited approach. What we believe, I believe planning is the art of dealing with temporal structures, and I think that the knowledge inference is something that has to do with properties, dealing with properties. If you want to create new algorithms for planners or knowledge of any type, neuronal, statistical, whatever, emergent, I really don't care about it. I just say there's probably two important structures that we can distinguish by the way reality is or how we perceive reality. And these two things together, they pretty much make up an engine, a motor. And so I claim that all cognitive architectures that I looked at basically somehow internally have these two components as like the core components. Maybe there's a few other ones around, but then if there's other ones around, then just imagine these other ones here, okay? I don't want to say there's only these two. It's not my point here I want to make. But what I want to make the point is there's a number of core components, and these core components make up an engine, a reasoning engine that is capable, that should be capable to make sense out of the sensor data we receive about the world, which is to a large degree video, but also audio or tactile or whatever. And so if these structures or subsystems make up an engine, then a self-representation, that's actually, sorry, slightly wrong here. The self-representation, or an example of a self-model, is when the engine takes a part of its structure, of the components of which is based the engine, and puts them on an object level. That means in the first order level, as I explained with the itch there, takes some part of itself into a representation, I would say, that's our take, into a representation, so that it then can take this representation as an input again and work on this representation. So self-referentiality, and the key that I believe on the self-referentiality is that the engine is looking at parts of itself. So let me see the other one. Yeah. So what in scene-based reasoning, yes, please. Yeah, evolutionary perspective. I think this is, well, I need to get some core concepts through. Would it be possible to ask that later on because evolutionary perspective is like, yeah. Okay. Do you want me to, well, you're getting the first question. So we got this engine with parts of itself represented on the object level, and then so that the engine will be able to process this itself. And in our cognitive architecture, we invented in the entire workshop. Okay, yeah. This is really the core here. Yeah. So I'll explain the 11 levels, so we don't really need to go in there. Perfect, thanks. So in our scene-based reasoning, we define the scene as a single unified representation, a very powerful one. We need to go into this in detail, in technical detail, if you want to understand how it works. A single representation for all of these different subsystems and their data structures. So this is the best of breed approach, and in order to get everything in one piece, we try to have a unified representation, so the actual data structure in the subsystems can be different, like heterogeneous, best of breed. Like planner talks about plans, reasoner talks about knowledge networks, the body talks about like 3D, whatever scenes. They're all in a single unified representation. Now, for example, with NARS, there seems to be a different approach. So instead of having one representation, they have one formalism in which they can represent all of these elements, or at least these elements where NARS exhibits self-models or self-referentiality. Single representation versus single formalism. I'm just saying, I was looking at the NARS scene-based reasoning differences. So they got one language. The core example is they have a language that's capable to express planning. So basically it's what we would call more on the semantic network level.
It's just a semantic network.
Yeah, but it is capable within the semantic network formalism. It is capable to express these temporal maps as they're apparently called in NARS. So within this formalism language, they represent what we would call as a separate structure, which is a plan. So yeah.
I wouldn't use NARS as an example, because it's not right.
Okay. So I actually added this yesterday, so it's not a very deep thought. It was coming from the discussions. I just want to say, in order to show, to create self-referentiality, you somehow need to be able to work on pieces of the engine yourself. And we propose to do this using this unified representation, and others can do it in other ways. This is not the only way. This is my point. Yeah, there are other ways, and we're not the only guys who've invented that. So many other systems, or all four systems were, system guys I talked on this conference exhibited some level of that. So that's, I think, the good point. So in our case, what we propose is like a two-dimensional representation, like a graph, like writing diagrams on paper, like I do, in order to get sequences. So mapping, for example, in the case of a plan, or in the case here of a knowledge tree, of a class hierarchy, really draw this with bubbles and arrows on a piece of paper, and then apply graph processing algorithms on that, similar to the way how the visual system is looking at a rabbit moving somewhere, or a scene like with you guys. So the idea is the lowest common denominator of all these representations is a kind of diagram on paper structure, like a two-dimensional, three-dimensional structure. So this is why this is our specific take. So this is why we believe this is a unified representation that can represent any other element in the system in a special way, and then we can apply this motor on reasoning about these diagrams, like having one plan and another plan and putting them together, or taking one element from a plan, including it, replacing it from an element from another plan, or recombining things. So a single representation allows us to use a single engine on all of these levels. And that is our take on these 11 levels, so why they are different, why some of them depend on each other, why this motor core is first needs to be there in order to do anything else. And yeah, I think this is the core of scene-based reasoning on these 11 levels.
Not much time left for this workshop.
Yes.
It would be good to hear what other people have
One
to say
last point.
about self-modeling from their own perspective.
One last point that I'll take. The idea, together with Jose, of creating a self-model scorecard. So the idea is we take any list of levels, however you want to define them, and create some task-oriented tests on each of these levels, possibly inspired by language, possibly inspired by for social actions or so, and score them. So we could have like a self-referentiality scorecard for cognitive architectures. So I think this could be a way to structure the discussion in a new way, where and it would be interesting to see if there's like different lists of self-models coming out. And obviously, it would be interesting to compare cognitive architectures. Okay, that was my last point here. Thanks. Thanks for interrupting.